yeah, so, sorry, so v dot w, so this is going to correspond to the inner product. This is going to be the length, and this creature is going to be ai dot ai bar. Yeah, this is fine. This length is going to be this less than this times this. Okay, and these are real numbers, and they're bigger than 0, greater than or equal to 0. Okay. Am I missing something?
Just in the RK case, do we need to square the length?
Do I need to square something?
Oh, no.
No, I don't. Yeah, because yes, maybe. Let's see. This is the okay. Now I'm just this is a length, and this is the absolute value of the dot product, and the dot product here is this creature. Do I need a square? Okay, now I'm.
If you had written it as b dot v and w dot w instead of
Yes, thank you. Okay, good. Sorry, I'm just getting a little confused by my own attempts to write this in a different way. Yes, right. If this had been a v dot v, then there would be a square involved. Right. But I took the square root of both sides. Okay. Cauchy-Schwarz. Why do we care so much about Cauchy-Schwarz? Well, for one reason, this is an inequality that you often encounter in multivariable calculus, right? When you think about v dot w as being the length of that as being the length of this times the sine of the angle in between, then you see that this particular inequality is true. In the complex vector case, this actually arises, it's actually the basis in physics of the Heisenberg uncertainty principle. Okay. And basically the Heisenberg uncertainty principle says something about something in physics, right? About position and momentum, right? They can't both be determined with very much precision, and it's based on the Cauchy-Schwarz inequality. Okay, so let's prove this. What can I say about the proof? I'm going to do a slightly different proof than that in the book. Actually, if you're good, I might do two proofs. But I'll give one that's equivalent to one in the book, but maybe easier now that I've made this definition to digest. So let's think about vectors in Cn. Okay, so let's let, instead of writing, I guess here I'm going to use the A's and the B's. I'm going to let A and B be elements of Cn. Okay, so they're vectors consisting of the AI's and the BI's. Okay. So the first thing that I want you to notice is it's very clear that 0, it's very clear that the 0 is less than or equal to the following quantity. A minus YB in length squared. Now, I haven't told you what y is yet, have I? But it doesn't matter. Whatever this vector is, its length squared is bigger than or equal to 0, yes? And I'm going to pick y later on. Okay, I'm going to be that'll be my choice, right? And I'm going to do so in a nice way. Okay. Okay, here we go. What do I do with this? Oh, well, this is easy enough to write as the inner product of A minus YB. And if you don't mind, I'm going to stop running the vector symbols for now, because it just makes this a lot more to write. It's the inner product of A minus YB with itself. Okay. Oh, okay, but what's that? Well, the inner product, I mean, it basically everything here is linear. This is a bilinear form in each of these entries. Everything just expands in the natural way if you just look at this definition. So if I want, I can rewrite this as the following. This is A, comma A, minus Y bar, A, comma B, minus Y, B, comma A, plus Y, absolute value of Y squared, B, comma B. How did I do that? If you like, I would put the intermediate step in. This is just, here if it helps, this is just the sum of A minus YB times A minus YB bar, everything barred. So sorry, these are vectors, right? So these are all the sums of the coefficients. These are the i's. Okay, I'll let you carry out the rest, but this is sort of this is where it comes from. You can rewrite it like this.